Hello everybody, welcome to section 4.3.2 where we'll be looking at data fitting using least squares approximation. Alright, so here's the setup. We're given observed data point x1, y1, x2, y2, xn, y1. That could be in a lab, in an experiment. I want to find the curve of a chosen type which best fit the data points. Alright, so this is something that you would do as part of your lab report, for example. So in this section, we'll use the method of least squares to find the best fitted line or parabola or cubic or so on to some given set of data points. Let's first consider the case of the best fitting line. All right, so let's assume I have all of these data points. These points would be on the line whenever, well, y1 has to fit the equation with x1. Y2 has to fit this equation with x2 and yn with xn. All right, so if they were actually on the line, this system would have one solution in AB. All right, so let's try to write this as a system with AB as a variable. So the first one would be 1x1, so A plus x1b, 1x2, and then 1xn. So I'm going to call this matrix M. All right, so we have a system, and usually that system right here or right here would be inconsistent. Because of error in measurements, you don't expect the points to actually lie on the line. You just want the line that's closest to containing these points. So let's apply this method of least square approximation to get something that's as close as possible to a solution to get the best possible A and B. All right, so find the least squares line fit to these 4 points. I have 1, 3, 2, 5, -2, and 3, 3. So I want to look at the system. So I want y1, y2, y3, y4. And that would be all the y, so 3, 5, 6, 3. All right, so that plays the role of the constants in the least squares. And then I want the matrix M. That's going to be 1x1, 1x2, 1x3, 1x4. So that's 1, 1, 1, 2, 1, -2, 1, 3. All right, so we have a system. 1, 1, 1, 2, 1, -2, 1, 3 times AB equals 3, 5, 6, 3. And we're going to apply least squares to that system. So I'm going to look at MTM. That's 1, 1, 1, 1. 1, 2, -2, 3 times 1, 1, 1, 1, 1, 2, -2, 3. All right, I get 1, 2, 3, 4. I get 1 plus 2 plus -2 plus 3. I get 4 again. Again 4, and then 1 plus 4 minus 4 plus 9. That's 18. Wait. 1 plus 4 plus 4, so that's 9 plus 9, 18. Yeah. All right, so that's the matrix of this associated normal system. I'm going to look at MTY. Remember, y is playing the role of the constant vector here. So 1, 1, 1, 1, 1, 2, -2, 3. And then y was 3, 5, 6, 3. And so I get 3 plus 5, 8, plus 6, 14, 17. And then 3 plus 10, that's 13, minus 12, that's 1, plus 9, that's 10. All right, so this system that I have to solve to find the least square approximation to A and B is this one. I've actually already simplified it for us, and I got 19/4, and I got minus a half. All right, so that's the best combination of A and B to get close to the line. So A star would be 19/4 and B star would be minus 1/2. And so that means the best line would be y equals, let's remember what A and B were. We're looking at A plus bx, so that means A plus bx. All right, and here's the line. I actually drew the 4 points. Here's the line that's closest to them. We're actually minimizing the distance going straight down from the line to the points. All right, so let's recap this method because you'll have to know how to apply it to any polynomial, but the logic is the same. If I have points x1, y1 to xn, yn, to find the best least square fit, something like this, in polynomials of degree m, right? So we did degree 1, but you could do any degree depending on what you're trying to model. All right, so you take y, that's going to be all the y values of your points. M, well, when we used a line, we just plugged in x1 in the formula. So that's the same thing we'll do. We're plugging x1 into this. That's going to give the coefficient of a0, an. So our variables are a0, a1, a2, am. All right, so I'm going to get always a 1 for the coefficient of a0. I'm going to get whatever x I'm using for the coefficient of a1, x1 squared, and x1 to the m. And then you do this for each of the data point, xn, sorry. All right, you then apply the method of least squares to the system y equals mv, and so solve the system. Remember, you just have to multiply it by the transpose. All right, if the least square solution is v star is a0 star through am star, then the best least square fit is a0 star plus a1 star x. All right, so what you obtain are the coefficient in the same order that you used here. All right, so that's the method. You probably have used it before without knowing in a lab.